All right, so this is part 3 of the section 8.1 videos, and we'll finish up 8.1 in the next few slides. All right, so we have talked about describing the sampling distribution. We've also talked about finding the mean of the sampling distribution and the standard error or the standard deviation of the sampling distribution. Now we're going to talk about the central limit theorem. That's a little bit different. So for the mean and standard deviation that we talked about in part 2, that's going to be true. That mean of the sampling distribution will be the same as the mean of the population, and the standard error or the standard deviation of the sampling distribution will be the same as the standard deviation divided by standard deviation of the population divided by the square root of the sample size. So that's going to be true no matter what. The central limit theorem takes it a step further and helps us finish describing the sampling distribution, but we have to have one of two things true in order to apply the central limit theorem, and we'll talk about that in this video. Alright, so we just saw in the previous video some sampling distributions, and I'm going to add those here. So we saw a sampling distribution from a sample of size 2, and that looked like this. Remember, there was that little extra piece of data out here that kept us really having still a very skewed distribution. And so I'm going to set that over here to the side. So we saw that was n equals 2. And then we saw what happens if we went to n equals 4. Well, here we go. Let's see. And let me make that. Oh, I'm going to try and make, there we go. Make that a little bit smaller. This one looked a little more bell-shaped, but of course we can see that there's still some extra data coming along more to the left side than the right. And remember, our parent distribution, the parent population, was very left skewed. So we're seeing, n equals 2, here was n equals 4. Then we looked at n equals 16, and here is our n equals 16. It started looking a lot closer. I think that's our n equals 16. I'm not going to mark it yet. I'm going to open up the other one just to make sure. Yes, that was n equals 16. And then here was our n equals 36. So let me mark those. And so what happened as our sample size increased? All of these were based on a simulation of 1,000 samples. So in order to get the blue, the blue bars, those heights represent numbers based on 1,000 simulations, and that's true for all 4 of these graphs. So we had the same number of data points, but our distributions became more and more bell-shaped. So here we still had just a little extra coming on over here, and a little bit of an empty space to the right-hand side. But then once we get over here to our size of 36, that started getting more normal, and everything's kind of fitting either within or very close to that black normal curve that is there to help us see what would the normal curve be if we use the mean and standard deviation or standard error that we found theoretically. So what is this? Well, this is what we call the central limit theorem. All right, so the central limit theorem says that regardless of the shape of the underlying population, so it could be normal, uniform, skewed one way or the other, or just something crazy, regardless of that shape, the sampling distribution of the sample mean, which is, of course, x bar is the sample mean. So the sampling distribution of x bar becomes approximately normal as the sample size increases. And we just saw that on the previous screen. So as n got bigger, we started with n equals 2, we went all the way up to n equals 36, and we saw it go from being somewhat skewed left to less skewed left, almost bell-shaped, and then at n equals 36, it was truly bell-shaped. And so that's what our central limit theorem says. Regardless of that beginning shape of the population. Now, of course, we started with a skewed population, a skewed distribution. So it didn't matter. As our sample size increased, we finally got to a bell-shaped sampling distribution. One thing to note is that the central limit theorem does not include the mean and standard deviation that we talked about, or mean and standard error of the sampling distribution that we talked about previously. So the central limit theorem which sometimes we might say central limit theorem. We like to abbreviate stuff because it just makes things easier. So the central limit theorem only addresses the shape of the distribution, of the sampling distribution. Not I don't know what happened. I'm not writing anymore. There we go. Not the mean or standard error. So that's a really important thing to remember. Some people think that the mean and standard deviation that we talked about in the previous video, the mean of the sampling distribution being equal to the mean of the population, and the standard error being equal to the standard deviation divided by the square root of n. Those are true, and we use those together, but the central limit theorem only talks about how that will get more normal as our sample size increases. So, you know, some people usually ask, like, how big does n need to be? Well, it depends. There's not actually one number that is the go-to number. There is a number that we will say we can be sure of. But I believe in your interactive assignment, I think, if I'm remembering correctly, they showed you what if you started with a uniform distribution. Well, you can end up with a bell-shaped curve with even just a sample of size n, because you're starting out with something that's not skewed. A uniform distribution, you're just going to get random numbers between maybe 0 and 10, and then if you take a sample size 4, those are going to end up being fairly normally distributed pretty quickly. If you have a normal distribution, you can actually ignore the sample size. Any sample size will work. If you start out normal, any sample size you take that sampling distribution will continue to be normal. But if we don't know what the underlying population looks like, if we don't know the shape already, or if we do know the shape and we know that it's skewed one way or the other, or perhaps bimodal. So there's, let me see if I can scoot this up just a little bit so I can draw. There we go. There's, some shapes that we didn't really name them or talk about them, but, there could be a shape that looks kind of like this. And what happens when I draw samples from something that looks, kind of like this shape here? Well, eventually, depending on my sample size, I'm going to end up with a normal sampling distribution because I've taken a large enough sample. So we don't have to worry about what size or what shape we start with, as long as, and this is typically kind of our go-to number, as long as we set n, or we know that n is greater than or equal to 30. Now, some textbooks will say 25, other textbooks will say 35. I think this textbook goes with n being greater than or equal to 30. So as long as we have 30 or more in our sample, then we're good to go.